A uniform plank, 2 meters in length, that is this object right here, with mass 4 kg is pivoted at one end. The plank is held in equilibrium in a horizontal position by a weight, that is this weight, and a pulley, as shown in the figure. Determine the weight W needed to balance the plank. Friction can be neglected. First, let's look at the free body diagram of this object. Why that is the case? Because that would reveal the value of tension in that strain. So there are two forces acting directly on this object. One is its own weight, which is W, and the other one is the tension in the strain. So we know immediately that the tension equals the weight. Next, let's look at the free body diagram of this plank. This is a uniform plank, so the weight acts exactly in the middle. Since the mass is 4 kg, the weight of that plank is 4 times gravity. So this distance here is 1 meter, and that is 1 meter. Now the second force. The second force is the normal force from that support, acting in an upward direction on the plank. So it goes like that. Let's call this normal force N. And the third force on that plank is the tension in the string that connects that plank to the pulley. And this value of the tension must be the same as that tension because they are the same rope. And the direction of this tension force on that plank is like that. Now let's calculate the torque about that support point. And this is the torque resulting from the forces acting directly on the plank. There are three, as we know: the normal force, the weight of the plank, and the tension. And since this plank is held in equilibrium, the sum of all these torques must be zero. So there are three contributions. Let's begin with the torque due to the normal force about that point. Since the normal force acts exactly at the point about which we want to calculate the torque, then the torque due to that normal force equals zero. There is no contribution, because after all, the magnitude of the torque is given by the magnitude of that force times the magnitude of the moment arm times the sine of the angle between the force and the moment arm. So since the moment arm is measured from the point about which the torque is to be calculated to where the force is, and in the case of the normal force, it is situated exactly at the point about which the torque is to be calculated, that would make the moment arm zero, and therefore the torque contributed by the normal force about that point is identically zero as well. The next force is the weight of that plank. And the torque due to that force, let's call that tau 4g, and it's given by the force 4g times the moment arm. The moment arm for that weight 4g is that distance, namely the distance between the point about which the torque is calculated to where the force acts. So in this case, it's 1 meter. So it is quite simply 4g Newton meter. And one final torque is the torque due to this tension on that plank. So the torque due to that tension equals the value of the tension times the moment arm, and for that case the moment arm is the entire distance, namely the distance between the point at which the torque, or about which the torque is calculated, to where that force acts, namely in this case the tension. So that distance is 2 meters. One other thing is sine of the angle between the moment arm and that force. So in this case is 45 degrees. So sine 45 degrees. We note here when we calculated the torque due to that 4G, that angle is 90 degrees, so sine 90 is 1. So we did not write anything there, it's just 1. So there we have it. We have 3 values, 1, 2, and 3. They all must sum up to 0. We note that the direction of that torque due to that 4G force is coming out of the board. So you can represent it with a dot. And the torque, or the direction of the torque due to this tension force, is going into the board. So what that means is, if this value is positive, then this value has got to be negative, so that when you sum these two numbers, you get 0. This torque is already 0. So let's sum them up and equate that sum to 0. So the first torque is 4G, the second torque is 2 times T, that's this one, times sine 45. Sine 45 is 1 over square root 2, and the sum equals to 0. Now we also know that this tension from this line is quite simply the weight of that object. So we can simply substitute that T as the weight, and from this equation the weight can be determined, which is what we want to determine. Determine the weight needed to balance the plank. Solving for W, we get 4G times square root 2 over 2, which is quite simply 2 times square root 2 times G. G is 9.81 meter per second squared. And that solves the problem. Problem 2. A ball of radius 4 cm and mass 2 kg rests on a plane tilted at an angle of 30 degrees. So that is the plane. So it makes 30 degrees with respect to the horizontal and also touches a vertical wall as shown below. So the ball is in contact with the wall and also with the plane. Assume that both surfaces have negligible friction. Find the force with which the ball presses on the wall, right there, and also the force with which the ball presses on the plane, right there. So let's label all the forces. The obvious force is the weight of that ball, which is vertically downward. We know that it is just 2 times gravity because the mass of that ball is 2 kg. The second force is of course from the wall, and that is the normal force, and it's acting like that. Let's write that as F sub W. And the third force is the normal force from the plane onto the ball, and it's going like that. Let's label that as F sub P. In this problem, it's sufficient to just look at the forces and make sure that they sum up to 0. There are 2 components. One is of course the Y component, and then there is this X component. And the forces along these 2 components must sum up to 0. Let's look at the forces that is going along the Y direction. There are 2. One is the weight, 2G, which is vertically downward, and the other one is the Y component of Fp. So the Y component of that force Fp goes vertically like that, vertically upward. So let's figure out Fpy in terms of Fp. To do that, we need to figure out a few angles. Now, this is the same as that, so that is 30 degrees. That means this angle right there is 90 minus 30, so that is 60 degrees, because these 2 lines are perpendicular to each other. If that is 60 degrees, then this has got to be 30 degrees, because these 2 lines are perpendicular to each other. So what that means is Fpy is quite simply Fp cosine 30 degrees, and that equals to 2g. From that, Fp can be immediately calculated. It is 2g over cosine 30 degrees. Now cosine 30 degrees is square root 3 over 2. So that means Fp is 2g times 2 over square root 3, or quite simply 4 over square root 3 times the gravitational acceleration. and that is the first force, namely the force with which the ball presses on the plane. Next, let's look at the x component forces. Now there are two. One is F sub W and the other one the x component of F sub P. The x component of that F sub P is going leftward, thus opposing F sub W. So that means F Px, or the x component of that Fp, must be the same as F sub W. So let's calculate the x component of that Fp. It's going like that. We know that this angle there is the same as that. It's 30 degrees because it is quite simply a zigzag rule. And what that means is this angle right there is 90 minus 30, so that is 60 degrees. So immediately you see that Fpx is quite simply Fp cosine 60 degrees, and that is F sub W. Since we already calculated Fp, that is just 4 over square root 3 times gravity, and cosine 60 is just half, that would immediately give us the Fw force, namely the force with which the ball presses on the wall. And simplifying, you get Fw to be 2g over square root 3. And these two results solve the problem. Thank you for watching.